So to start off, I'll describe the lens through which I'm looking at these reactions. So I'm usually looking at the real-time dynamics in nuclear systems. And that is a very broad term, but there's a lot of things we can look at with these sorts of frameworks. Now, on the quickest types of reactions, we have quasi-elastic, where not much interesting happens, but this goes through multi-nucleon transfer. You can also study the fission of big compound nuclei or spontaneous fission. But the focus of today's talk, the star of the show, is heavy ion fusion. So in heavy ion fusion, what you have is you start off with two nuclei coming from somewhere far away. They come together, interact, and then you're left with a single compound that's a little bit excited after the whole ordeal. And the particular framework that I'm investigating, at least what I'm presenting today on, is that of time-dependent density functional theory. So we've had a lot of discussion on the DFT. I don't think there's been much discussion on DFT, but it's a relatively simple extension of the base density functional theory in that you just take your mini-body wave function and then you just start propagating it in time using the same geometry and EDF that you have for your DFT process. Now you do have all the benefits then. This is really nice because you have these structure effects that we've been talking about on the DFT side of things. So you do have these deformations, your prolate, hexadecapole, prolate quadrupole moments, your hexadecapole moments. In principle, you can go to higher order moments if you're really feeling pedantic that day. But it goes beyond just these overall bulk shapes. They're not just blobs. You have a lot of internal structure in these things. So you have sort of higher density regions that can form. It's not just saturating and then falling off monotonically.
Do you consider like quantum mechanical fluctuations in the nucleons as well?
So there are fluctuations at the one body level. The fluctuations, if you want to really do a study of like particle number fluctuations and these sorts of things, you have to extend the base theory. Yeah, they're not well reproduced in DFT by itself. And this isn't even getting into if you start doing crazy things with your DFT, doing constraints or projections. You can prepare weird shapes, excited states, whatever you like. And the nice thing about the time-dependent extension of DFT is you get all of these intricate structure features in your dynamics as well for free. You just take them along with you when you start time evolving. And once you're in the dynamic side of things, I'll just have this looping here. Indeed, you have the initial structure and shapes, but at the low energies, you also have these things that we start to care about in terms of like polarization, these collective excitations of the fragments as they approach, neck formation. In this case, there's a lot of bulk matter transfer happening between the blobs. But
what's that yellow?
that the yellow is a higher density contour drawn inside of the typical outer contour that we see. So it's just to show that there's a little bit more stuff going on the inside. And looking even further than just this picture of the blobs, if I make this a little bit larger, here we're also plotting the particle currents, which don't show up super well, but maybe you can believe there's something cool happening in the upper and the lower. The middle, though, is the classic picture of just the blobs. You see, in this case, what's going to happen is you have your fragment come in, they collide, and then eventually they separate. If you're just looking at the contours, it's really boring, actually, because it doesn't look like there's much going on. But there's a ton of currents and particles sloshing around, making these cool eddy current looking things over the course of this reaction. And sometimes that's what makes or breaks a fusion event, for instance. And then if we split things up even more and think like, okay, well, we have two different types of particles here, protons and neutrons. And there we go, this one's much better. And in this case, if we pause right when they start to interact, there's a large flux of protons one way, neutrons the other way. So there's not this entrainment effect. They do have minds of their own. They move in accordance to the dynamics of the system.
Are you plotting the gradient or this is actually, because you have some collision that coming with some speed?
Yeah.
Are they suggesting they actually leave the surface of one nucleus and go jump to the other, or they just gradient?
Yes, no, this is the total, this is the total current of the particle. And right now they're really slow because they've cool on to stop them, but they're starting to flow into one another here.
But they're also approaching each other. Can they actually flow ahead of the?
No, here there's a slight overlap, and this overlap, that's their little tunnel where they can start
So
to,
you just draw the current itself?
Yeah.
Not the actual density.
yeah, the density's just sort of in the background.
So
What does the color mean?
So protons are on the top, neutrons are on the bottom. So this is an example of isospin equilibration where we have this really neutron-rich calcium, and basically the isospin asymmetry gets equilibrated within the first couple zeptoseconds of the reaction. And then after that initial equilibration process, things start to slosh around, and this ends up leading to fusion. But for a second, it looks like it might not, and it turns out this equilibration is what makes it easy. We have a question in the back.
So you have protons and neutrons flowing in opposite ranges because you took those asymmetric systems, one neutron rich and the other one
Yeah.
proton rich. So if you had two neutron rich systems, for example, let's say instead of 1610, 13210, you would have neutrons flowing.
Yeah, so that is a great example because I actually have 10132 here. I don't have calcium 54, but for calcium 40, there is just a net neutron transfer that happens there. But you actually have like a sort of deadlock in the case of calcium 48. And so I wasn't going to get into the details of this, but I might as well. Sometimes these transfer effects can lead to enhancements or hindrances of fusion cross sections. So that's why we're investigating these things typically. So in this case, if you have a lot of transfer in your system, this tends to promote subbarrier fusion cross sections. It enhances the cross sections. But I just show this to say that these intricacies of the structure and dynamics aren't just fun little curiosities. They do have profound impacts on the observables of the systems. Yeah, cross sections, but also fragment formation, the energies of those fragments, et cetera, et cetera. Now, the only thing really, besides, of course, geometric considerations of your box and your energy of the systems, the only thing that defines these structure and dynamics is your energy density function. And we already had a talk earlier today that so there was a little bit of discussion about this EDF and the form of it. And what I'm showing here is the exact same EDF, just written a little bit differently with not as many energy terms. And you can really write down whatever EDF you want once you really embrace the phenomenology, the phenomenological aspect of DFT.
So what's the difference between the EFT and the EDF?
Yeah, so the energy density functional is, think of it as it's your force that you're solving your DFT problem for. And in this case, we have a skirm type EDF, it's a really popular one, but the form of the EDF doesn't really matter so much. You need interactions, you have people doing covariant energy density functional, they have their own bag of worms over there, but the core premise is the same. You have some functional, and I'll point with this. You have some functional that depends on things like your number density and your particle currents here, but also you have spin densities and kinetic energy densities and everything thrown into the mix. And what you do, I don't know why I'm not full screen, but what you do is you have all of these coefficients out in front of these different terms that are called coupling constants because they couple to these various densities, and you need to determine what they are. And the traditional method, and really the only method, if you're not deriving one of these from the first principles, is to do some fit to experimental data. Now, what you end up doing if you just do a single fit and find the best parameter given a set of data, you end up with all of these different things that are called forces. This is sort of a historical term at this point, in my opinion, where you have a bunch of alphabet soups, you know, SKM star SOI4D, that's one of my personal favorites, it's a really nice one. But these are really all just different parameters that define that same EDF that I showed before. So it's hard to say that they're really a different force or just a different set of parameters to do the same thing. So this is, you know, a little should be unsettling, I think, to plot just a bunch of these different forces, because again, you're pulling from the same distribution essentially. So it's really better, in my opinion, whenever you're talking about DFT, to think instead of some distribution of reasonable parameters given the data that's informing your model. And that is the core philosophy behind the work that I'm presenting today, and also sort of the shift I say that most practitioners of DFT are moving towards, this sort of quantified prediction overall.
May I ask a question?
Yeah.
So when you specify certain SCRM parameter like SLY14, right?
Mhm.
They come with fixed parameter because they are they were what do you call it, fit certain properties.
Mhm.
So then how do you put in a range of parameters?
Yeah, so the end goal is, instead of having just those single parameters, you end up with some distribution of reasonable parameters. And this is relativistic mean field, but just imagine if this were SCRM. The idea is, if you do your Bayesian calibration well, then SLY4D will live somewhere in this space.
Yeah.
Unit F1 will live somewhere else in this space. So to move beyond just a named set of SCRM parameters and say, instead we have a distribution of parameters that defines a given energy density functional as a whole. So treating the EDF as the object, as opposed to the certain parameters we define that EDF by, if that makes sense.
So part of this program, though, is to start from what are the observables that you want to fit?
Yeah.
And in my personal philosophy, whenever we're doing these Bayesian calibration, is to inform our models as much as possible, to take as much high quality data that we can, and that will then show up in your posterior distribution and give you the set of reasonable parameters. Okay. So what I am showing here is just an example of whenever we say we're doing UQ over in DFT, this is kind of what we're starting with. This is the result of our calibration. We have 5 million points that are sampled from our posterior here. We had a nice MCMC go dance around our 8-dimensional parameter space. And these are the posteriors we determined. And then what we do is we start sampling from these posteriors.
What are the two lines in the Martian distributions?
So the blue line that you can kind of see is the a Gaussian approximation that was done previously. So our posteriors are the black lines. And then you start making predictions, and this is what the plot on the right is really what matters at the end of the day. Whenever you want to put a data point on a plot of experiment, this is what you're going to be dealing with.
So you say that the blue lines didn't include all the uncertainties, and when you do it your way, you get a more reliable assessment of the.
Yeah, it's a more robust determination of the uncertainties.
Why did in previous studies not account for all the uncertainties?
What they did was they just did a basically chi-square fit and then assumed a Gaussian distribution around that. Yeah. But in the case of the project that I'm highlighting in this talk, we're instead working over in SCRM land instead of covariant EDF. But the principle is the same. We want to take these posterior distributions, sample some points from these parameters, and then make predictions, in this case, of cross sections. Now,
May I make another comment? Your previous slide, right?
Yeah.
So for SLY4, whatever that you are using as a part, my understanding SLY SCRM fit something to do with the neutron star. So it's not just these.
yeah, it's not just these.
So then how do you take into account of the extra stuff in the SLY4?
Yeah, so this isn't SCRM at all, this one here. This is a SCRM posterior distribution, which again, SLY4 probably lives somewhere in here. Whenever they did their uncertainty quantification study for this SCRM EDF, I don't think that they included any information on neutron stars here, but building.
Yeah, that's exactly right,
Yeah.
that you don't include it, but the original
Well,
SCRM does.
SLY4 does,
Yeah.
the group from France in 1998, when they had their SLY series, this is
Yeah.
what they included in their, informing their model. But ideally, what you do is you inform your model from as many sources as possible. This is ongoing research, building better EDFs, and that does include having the neutron star information included there too. Yeah, it's an active field of research, I would say. This, once you have this posterior, it's not frozen in time. You can always update it with new information. Yes.
Yeah, but when you do that, you give it a new name,
Nope.
but then SLY4 that you have is not the same as SLY4.
No, this isn't SLY4.
No, but I'm saying you have some label.
Yeah.
Some label relatively detailed or.
No. So in my personal vision of DFT, what you have is a continuously calibrated SCRM EDF that as new data comes online, you have this as your prior, you update it, get your new posterior, and whenever you want to do a calculation, you take the fresh, hot samples from the posterior, compute your observables, and then that's what you have. You could freeze this if you like and say this is SCRM 2023A, but yeah, that
I think if you want people to reproduce your data, you have to freeze it.
no, you can always have snapshots. Okay. So again, what we want to do is get fusion cross sections, and that is not an observable, or at least for subbarrier fusion cross sections, that's not an observable that's directly accessible within time-dependent density functional theory. So we do have to take a little detour along the way and compute some ion-ion fusion potentials such that we can look in the subbarrier region. But the procedure is still the same. You take some points from your posterior, you then do the static calculation of your collision partners, you collide them, you generate these ion-ion fusion potentials, and then the good thing, I guess, from the point of view of doing UQ is that they're not on top of each other, so there is some point to doing it. And then you take these potentials and compute your fusion cross sections with them. So again, there is some difference there. There's obviously some uncertainty on these observables within our model. So let's compare the data and see exactly to what magnitude it is. So in the case of calcium-40, the median line is the dark blue line, and then there is some shaded band that represent the other predictions from the sample cost from parameter sample from the posterior. And the core features that you see here is it's pretty symmetric uncertainties around this median line. And at least in this log plot, you see that it does start to grow a little bit and spread out as you go down further into the subarea region.
The line, the maximum of posterior distribution, or is it something?
This is the median of the predictions. Yeah. Now, so in the case of calcium-40 symmetric collisions, it seems like there's probably the principal amount of the uncertainty is coming a little from the initial state, maybe, and some in terms of the dynamics. In the case of calcium-48 symmetric collisions, you see that there's quite a larger band around these lines. So we get a lot more variation in our prediction of the cross sections. Now, this difference is actually pretty easy to understand where it's coming from. If we go back to the previous slide, if you look at these potentials, you see that where the difference starts to kick in is around the top of this barrier. And you see there's a few MeV difference between where the top of that barrier is. And thus, if you start changing what the top of your barrier is, obviously you're changing where the sub-barrier region starts. So the sub-barrier region is where this thing really starts to take a nosedive and go down on the log plot. So it seems like the primary source of uncertainty here is coming from our determination of the barrier top. And that's also, if we take another little leap in logic, pretty easy to understand for the case of calcium-48, because since this is a symmetric collision, there's not going to be any transfer effects that are enhancing the fusion in this case. And indeed, if you think as the calcium-48, and I think they can see them too, as the calcium 48 nuclei start to come a little bit closer, whenever they're the diffuse part of the neutron skin starts to overlap, that's when it will overcome the Coulomb repulsion and pull in and form this compound. So if you have a larger neutron skin in that case, then this is going to happen sooner and thus result in a slightly lower barrier top. So it seems like there should be some correlation then between the neutron skin thickness or the neutron radius of calcium 48 and the fusion barrier that we're producing in our model. But if we want to investigate this correlation, we'd really like to compare it to experiment, obviously, and a barrier height isn't something that you can measure. You can extract it, though, from the experimental cross-sectional distribution. Now, if you just are dealing with the data, then you can have some pretty rough-looking derivatives if you have coarse or irregular data. For calcium 48, it's actually not too bad. So you see in the bottom here that this first hump is pretty similar between the different spacing and energy that we're taking, but it would still be nice to have a little bit more control over this. So what I've done on this slide is taken our cross sections across our range of energy and you fit a Gaussian process to have some sense, or to use it basically as an interpolator, and then have some sense of our interpolation error of the original cross-sectional data here. And I know it's going to extrapolate horribly. In fact, you can see that there, but that's not where I'm working. This area right here is where we're looking for these structures. So you can sample a bunch from this GP and do the same derivative, but now you have a much nicer thing to take in the derivative of and produce a bunch of these barrier distributions from your interpolated cross sections. And then by taking the peak of all of these different distributions, then you can have some reasonable extraction with some interpolation error of this barrier quantity that we're wanting to compare. And now, then we have one for experiment that we can look at least for the barrier, and we can plot the neutron skin thickness coming from our model versus the barrier coming from our model and see if they're correlated. And indeed, yes, they are. In fact, there's a pretty strong correlation. This is the Pearson correlation coefficient here. And the black dots here are directly from the model simulations. And this red line hatched area is what was from the previous slide. So it does seem like there is a very strong correlation between the skin of your calcium 48 and the barrier height that you see in heavy ion fusion. And this is something you also see for things like non-symmetric collisions, calcium 40 on calcium 48. But the correlation is much, much stronger for calcium 48, obviously, because it's symmetric. And it sort of gives you a way to magnify this effect. So that's something that's going to be really exciting as effort lets us get to do heavy ion fusion studies with a little more rarer isotopes. But there are going to be some issues there because the rarer the isotope, the lower the rate, and you're not going to be able to do too much work in the sub-Earth region. So that's definitely still going to be a problem. And while having this constraint, so you notice quite a few points from our model were outside of our estimate from experiment. That does give us some constraint, but we would really like to include either barriers or cross sections in our calibration as well, because all of these results that I showed, all of these sperm EDFs have only ever been calibrated to at most maybe some resonances or fission barriers, primarily usually the static properties. Yeah.
Yeah, so before you go into the next one, so what about the calcium 40 and calcium 40? You showed the calcium 48.
Yeah. So I showed calcium 40 before, and
On the, no, I'm talking about the
on the correlation.
Yeah.
Yeah. So the skin of calcium 40 is not that interesting. And you don't really see too much going on for that. Yeah, in this case. There may be other things you can look at, but skin, nothing there. So even though we'd like to do full calibration with these dynamical qualities, Sheeling talked about all these great advances in emulation that have been sweeping the field in recent years. But while yes, it's great, you have these RVMs that give you millions and millions of samples, they're not really great for time-dependent problems. Yeah, don't get me wrong, you can use them, but for looking at the translation of this density or this many-body wave function in space, RVMs don't work great for that. So it's likely that we're going to have to do things that are a little more exotic. So there are a lot of
What does RVM stand for?
reduced basis method.
Oh,
So it's likely that we're going to have to use more data-driven approaches to get at the real-time dynamic simulations. And this includes, there are a couple of techniques, you can look them up later if you pull my slides from the website. But even with robust, accurate emulation of these time-dependent problems, it's still possible that we're not going to be able to get to the sampling rate we need to do this direct Bayesian calibration. So to that end, we've been working with our applied math colleagues, statisticians, to explore things like polynomial chaos expansion, which is like a reduced basis method for your random distribution, which we hope at least, it seems promising that we can reduce the number of total samples by at least an order of magnitude, maybe two, but this is very speculative. So maybe by next workshop, we'll have something cool. Yeah.
So what's wrong with simple Gaussian process emulators? They're not accurate enough, and how do you see it?
So you can use Gaussian process, obviously. We've never explored it for if it can capture all of these intricate nonlinear dynamics and all the observables that we're interested in for the time-dependent simulations. I mean, it could be explored definitely, but direct model emulation is at least a little more intellectually pure, perhaps. I don't know.
Yeah, but if it costs you a lot of computing time,
Yeah, that's about. Another reason we are interested in doing this, though, is of course for systematic studies where where it's easily parallelizable, and also for deployable emulators. So if we have these time-dependent emulators, we do the development on them, we can put it in a cloud computing infrastructure, and anybody can use that emulator for their own purposes. So there are other reasons besides UQ that we're investigating. And then I'll come to the conclusions here. So the conclusions are a little more general. The first one is that if you are interested in low energy reactions, energy reactions, if you're interested in trying to link these structure effects and look at all these cool shapes and stuff, you should really take care to remember that these models are not perfect and they never will be. And you will have some uncertainties there that you should propagate through your entire analysis. And then also all of these intricacies that we've been talking about, those are all influenced, of course, by those uncertainties. So the shapes, maybe what you expect should be spherical. If you start going crazy in your parameter space because you don't have any way to constrain it, now it picks up these weird deformations and such. So don't just consider a little band, but consider that things could get drastically different. So with that, thank you very much.
Questions?
So how do you mean whether, are there any principles, rules you need to follow, or just,
Whenever you're building an EDF, well, there's many ways to do it. So the SCRM EDF, for instance, was derived from the SCRM effective interaction, and with a few tweaks along the way to make it work for nuclei. But over in
is there a general procedure?
you can systematically expand like a density matrix expansion and construct an EDF, but over in condensed matter, what they're doing is just finding out what works and doing symbolic regression, for instance, and inventing things that way.
So, when I was fitting SCRM functionals to binding energies, I found that there were local minima that didn't talk to each other very much, which means that there was higher order correlation between the parameters. Do you see any of that kind of stuff in your Bayesian?
Yeah, so all of the parameters are very correlated. If you did a scree plot, for instance, and looked at the principal components of these parameters, you'd see that they're not all independent. So they're definitely correlated. As to the level of these correlations, it really kind of depends. I would recommend looking at the original Unit F paper if you want to see the extent of like the strength of the correlation.
But when you show these two-dimensional plots,
Yeah.
it's just pair correlations between the parameters.
Yes, they are all correlated.
Yeah, okay.
Yeah, you have this 10-dimensional space, they're all correlated.
We have a question online. Zito, can you unmute?
Yeah. So first, thank you so much for the interesting talk, Kyle. So I have a question about this method. So I'm interested in the dynamics that you mentioned. So because while we are calculating the fusion cross sections, so maybe so actually we have a simpler method to calculate the fusion cross section, which is simply to use energy barrier penetration model and use those frozen densities of those two nuclei, and we can still calculate the fusion cross-section. But in this way, we don't care about the dynamics. Have you ever tried to compare your calculation with that kind of the simpler method by using the frozen density?
Yes, extensively. So if I don't talk about it here, obviously, but if you use the frozen density just all by itself, just start overlaying densities on top of each other, then you start to have a lot of issues with the Pauli exclusion principle. And so if I'm guessing, if you look at your potential, it's going to go down to infinity, basically. So if you add in Pauli, so if you do some minimization, then you can get a pocket, but that's still going to be not a great representation because the collective excitations during the collision are very, very important. So net formation in this rearrangement leads to a much less stiff potential. So that's the main issue with the frozen approach is you're kind of assuming infinite energy in that case. Or collision.
Yeah, right, yeah. So, okay, so I have actually my second question is that, do you think that kind of the dynamics or something like those time-dependent effect will be somehow relating to the neutron richness of that nuclei? For example, maybe the dynamics effect will becoming more and more important when you have a more and more neutron-rich nuclei?
Yeah, so there's not a simple relation between these, but yes, certainly. If you're talking about just the collective excitation of the partners, then yeah, if you have more neutrons, then there's going to be a big difference than if you have less neutrons. But also from the point of view of transfer effects, if you have something that's really neutron rich and something that's really neutron poor, you'll have a large flux of these neutrons one way, protons the other.
Okay.
Yeah,
I see.
yeah.
Okay, thank you so much.
Betty?
Yes, so you are using the SLY4, right? So then what if you change it to, I mean, whatever.
Okay. Yeah.
If you use another family of the SCRM, there are many families,
Well,
then what happened? I mean, do you get the same?
so this is using SCRM totally. It's not using the SLY series, it's just using SCRM.
Oh, I see. So
Yeah.
you just put a,
SLY4 lives somewhere in that distribution. Yeah.
I see.
Those
So you
some-
have a general,
It's, yes,
also parameters that you use, I don't know, 11 or 13 of them.
yeah,
That you put a range on them. And
yeah, from the posteriors that I showed earlier. Yeah. Now, things would be different, of course, if I use a different function. So something that's not skirm at all, if I use
Yeah.
beneath, for instance.
Did you say something about relativistic mean field?
Yeah, we've not done the dynamics in that. We just did a calibration for the static relativistic mean field, but it's another energy density. It's another density functional theory approach, just a little different.
So you showed this correlation between the neutron skin thickness and value.
Mhm.
Now, when you have fusion, as you were showing in the movie at the beginning, you have some polarization of the nuclei, and so that's distorting
Mhm.
the ground state. Therefore, your fusion cross section from which you are actually extracting this should be influenced by this amount of polarization. So then my question is, don't you think you will have more uncertainty in relating to the neutron scale in the ground state?
Yeah, so one, the polarization isn't too strong, but it could be looked at. But this R skin value is taken from the ground state. So we take this, and then the other observable that I'm looking at is the V bear.
So my point is that maybe this relation has more uncertainty because you're not taking into account the effect of polarization.
Polarization gets taken into effect in the V barrier. So as I collide them, if there is some slight polarization, that will be there.
So if not, I have actually some questions.
Yes, sir.
So, one thing is it seems like you're limited basically by what you can get from the experiment. And so you get a cross section of the barrier. Is there any chance with the future of effort that you'll have new experimental observables that you can compare to and further constrain your model?
Yeah, so in terms of new observables, I don't think, I can't think of anything off the top of my head here right now. It would be really nice though to just get more data, get the same observables from more data. I could do the same analysis with just taking 1 point from the cross section and saying, oh, here we use this as our constraint. But I like the barrier a little better because it includes sort of a series of points.
And then I had another question, and this is more like what else you could do with this.
Yeah.
Is I know that a lot of people do stuff like rate equations to understand nuclear synthesis, might
Yeah.
how that goes up another chart. Could you do something like, could you do sequential interactions with this? Like,
No, that would require sort of a secondary step. So like what could be done, for instance, is what has been done is, say I produce fusion cross sections for carbon. And then you take those cross sections and then you put them into one of these calculations that does the rate equations.
okay, but you can't just like do one thing and then collide with something else. And
No, I mean, I could, but I don't think it would be too instructive.